Hello everyone, my name is Emmanuel Carlton and this is the first video on Laplace Transforms. Alright, so I'm going to take you through Laplace Transforms, a quick introduction, and then show you how to find the Laplace of a constant. And also we will learn how to find the Laplace of the exponential function. Alright, so quick history. The Laplace transform is named after a mathematician called Pierre-Simon Laplace. He used a similar transform in his work in probability theory. Now the Laplace transform is an integral transform. It converts a function of a real variable, often time, to a function of a complex variable, S. We denote it by S. It is termed a complex frequency. Now, the Laplace transform is very powerful, very, very powerful. It has many applications in science and engineering because it is a tool used for solving differential equations. What it does is it transforms differential equations into algebraic equations and then convolution into multiplication. All right, I think that is enough for the introduction. So we'll start with the definition of Laplace transform, which is very important. Transforms. All right, so the Laplace transform of a function. The Laplace transform of a function. The function is usually denoted by f of t, defined for t greater than 0. Okay, so the Laplace transform of a function f of t is actually defined as L, capital L, f of t. So this is how we denote Laplace transform of f of t. This f of t is the function we want to transform. Okay, we can also denote it by capital F of s. This x is actually an arbitrary positive number. We use this x here because the result or the transform will be a function of x. That's why we have this. So you could also denote this, the Laplace transform, by this. All right, and then also with this one, you could use the curly bracket, or you could also use a square bracket. It all works. All right, so the Laplace transform is actually defined as the integral running from 0 to infinity f of t e to the power minus xt dt. Okay, there's an important condition attached to it. This x is always kept positive. I'll show you why it is important. This x has to be positive in a bit when we are finding the transforms of a constant and the other functions. It is very important this x is kept positive. Okay, so this x is actually an arbitrary positive number. It is chosen so as to ensure that the integral converges. Okay, if this x is negative, the integral will not converge. Okay, if it's 0, the Laplace will not be defined. Okay, it will not be defined, so it won't be convergent. All right, so this condition is very important. Now, just take note that this integral we are using here is an improper integral. Now, a prerequisite topic for Laplace is improper integrals. But I'm going to take my time to go through this systematically. So I'm sure everyone is going to benefit with this, even if you don't know how to work around improper integrals. Okay, so just know that this is an improper integral. Okay, so I want to start with finding the Laplace of a constant A. Finding the Laplace transform of a constant A. Okay, so it means that our function here is A. F of t is A. So we are going to look at how to find the Laplace using the definition here to find the Laplace transform of any constant. Okay, in this case, A. All right, so I'll first put down my definition. So the Laplace of f of t is giving us an integral running from 0 to infinity f of t e to the power minus st dt. Okay, so in this case, what our f of t here is A. So all we do here is we plug in A in place of f of t. So we have the Laplace of A equals integrals running from 0 to infinity A e to the power minus st dt. Okay, all right, so the next step is we just evaluate this integral, which is very basic, but I will take my time. I'll do it systematically so that everyone benefits from this. All right, so now to integrate this, let's take note that this is a function of t. It's actually with respect to t. So this a here is a constant, so we can pull it out. So a can come out, and then we have 0 to infinity e minus st dt. Okay, so we take the integral of this. Now to integrate an exponential function, all we do is we differentiate the exponent, the power, okay, and then divide this function by the result. Okay, so what we do when we do this, when we differentiate this, we have minus x, and then we divide it by this. So we have e to the power minus st all over minus x, and then we attach our limit e to the power infinity. Okay, so now we want to, the next step is to run your limit through, you put your limit into the function here. Okay, so let's take note that the function here, the variable we're actually considering is t. Okay, so it means that this minus x is actually not important here, so we can pull it out. So we can pull this out and have minus a over x outside, and then have e to the power minus st. We can have this. Okay, so the first thing I do is I'll put in my infinity. When you put in infinity in place of t, you're going to have e to the power minus infinity. Okay, and then e to the power minus infinity is what? The limit as this approaches infinity is 0. Okay, minus, the next step is we put in our 0. This becomes e to the power 0, which is 1. Okay, sorry about that. Just 1. Okay, so this becomes minus a over s multiplied by 1 times 1. So this becomes a over s. So what this actually means is that the Laplace of a, where a is a constant, is actually a over s. Now, I want to put this condition, provided s is greater than 0. Okay, so what we're actually talking about here is that this actually implies that the Laplace of a constant, any constant, it's actually the constant over s. It's that simple. Okay, so I'll put in some examples. The Laplace of 5 is actually 5 over s. The Laplace of 85 is actually 85 over s. The Laplace of minus 2, sorry, it's actually minus 2 over s. The Laplace of 1028 is actually 1028 over s. So what this actually means is that the Laplace of any constant is actually the constant, the constant over s. Okay, the constant over s. So I want to quickly explain this part, why x is always kept 0. Now, sorry, why x is always kept positive. Now notice that x is greater than 0, it's demanded. Okay, in this case, because if x is less than 0, then this integrand, that is e exponent minus st, will approach infinity as x approaches infinity. Do you see that? Okay, so the reason why x is very important and x is greater than 0 is that if x is less than 0, okay, then right here, in place of s, if you put minus x, the minus is going to nullify this minus, and then you're going to have e exponent xt. Okay, so you're going to have e exponent st here, and then when you put in the limit, e exponent st is going to be e exponent the limit as this approaches infinity is going to be e exponent infinity, which is infinity, not 0. Okay, so right here we are not going to get 0, we're going to get infinity. So this is why this x is always kept positive. Okay, so that our integral will converge. So it's very important that this s is kept positive so that our integral converges. Now, in the same way, if s is if s is 0, the Laplace is going to be, the Laplace of a is not going to be defined. Okay, so in both cases, the integral diverges. Okay, so it is important that the x has to be kept positive. All right, so this is how we find the Laplace of any constant. So the baseline here is that the Laplace of any constant is the constant over s. The constant over s. Okay. Now I would want to talk about the Laplace, finding the Laplace of the exponential function. Okay, so we want to look at the Laplace of EAT, where a is a constant. So just like we did for the Laplace of a constant, you're going to use the definition to find the Laplace of the exponential function. So right here, our function that is f of t is what? E to the power at. Okay, so just like we did, we put down our definition for Laplace, giving us integral running from 0 to infinity, f of t, e to the power minus st dt. Okay, so all that we do is in place of f of t, we put e to the power at. So we have the Laplace of e to the power at. And then we have integral running from 0 to infinity, e to the power at times e to the power minus st dt. Okay, now right from here, the next step is we use indices to put these two expressions together, and then this gives us e to the power at minus st dt. Okay, so the next step here is that what we do here is we factor out t and we factor out negative. This is because we want this integral to converge. And in order to do that, we want to keep a negative sign out. Okay, so this is what we are going to do. This part is very important. So we're going to have the integral run from 0 to infinity e to the power minus outside bracket and s minus a t. So you factor out t out, you factor out t, and then you factor out minus sign. Okay, so that you can have this dt. Okay, now the next step is we do our integration, and then we first differentiate the power of the exponent, and then you divide it by the whole. You divide the result. Okay, so you have e to the power minus s minus a t over, when you differentiate this, you have minus s minus a. This runs from 0 to infinity. Okay, so just like we did for the Laplace of a constant, we pull this one out. Okay, so when we pull this out, you have minus 1 over x minus a out, and you'll be left with e to the power minus s minus a t 0 to infinity. Okay, now when we put in our limits, when you put in your limit, this becomes e to the power minus infinity, okay, which is what? 0 minus, when you put in your limit, that becomes e to the power 0, which is 1. So this gives us minus 1 over x minus a times minus 1. So this becomes 1 over s minus a. Yeah? Okay, so this tells us that the Laplace of the exponential function is actually 1 over x minus a. That's simple. The Laplace of the exponential function is actually 1 over x minus a, where this a is any constant. So with this, we can find the Laplace of any exponential function. Let's do that. So the Laplace of e exponent 2t is what? 1 over x minus 2. Over here, a is what? 2, so you just replace it here, that's all. So when you're asked to find the Laplace of any exponential function, knowing this formula, that is 1 over x minus a, there's no need to go through the long integration. All right, you just replace this one by a, and you have your Laplace. In the same thing, let's find the Laplace of e exponent 59t, and that is 1 over x minus 59. The same idea, Laplace of e exponent minus 5t gives us 1 over x minus 5. And remember that a is what? Minus 5. And this becomes 1 over x plus 5. Okay, so I want us to summarize everything we've done today. Quick one, summary. We looked at the definition of Laplace, and then we said the Laplace, which is denoted by, Laplace, which is denoted by Laplace of L, capital L of ft. You can also denote it by capital F of x. It's actually given by integral running from 0 to infinity f of t e to the power minus xt dt. X is greater than 0. That's the first thing we learned today. So this is take home. All right. The next thing we looked at is finding the Laplace of a constant. So we saw that the Laplace of a constant, which is a, is actually a over x. So the Laplace of a constant is the constant over x. Okay, so with this, when you find the Laplace of 29, this is 29 over x. Okay, and then finally, we looked at the Laplace of the exponential function, e to the power at, where a is a constant. Now that this is 1 over x minus a. And then with this, we can find the Laplace of e to the power 5t, and this is 1 over x minus 5. So basically, this is what we've gone through today. I don't want to make this video that long, so I'll stop here and then continue with some other important functions in a new video. All right, so the next thing I'll talk about is finding the Laplace transform of the sine of at, the cosine of at, and other important functions. So stay with us, and don't forget to like and subscribe for more videos. Thank you so much. Have a nice day. Bye.